Do I need
Give me a second. What is this thing of reconnecting?
these are the subtitles. I can turn them off. Okay.
Yeah. So let's start. So for me, it's a pleasure to introduce Eric Burkholder. He has been here before. Now he's part of the family. He's helping, or at least I want to think from my side that he's part of our academic family. He's helping a lot to use these methods of active learning applied to our teaching, in particular now in physics. And he's here this week to give this the third workshop on active learning, and he kindly agreed. Actually, he volunteered. I didn't have to tell him anything to give a seminar, which is entitled "Can we make science more accessible by teaching real-world problem solving?" So, thank you very much. Yeah, and please go ahead.
Yeah, thank you. So, okay. Good. Oh, except now, what happened now? My PowerPoint closed somehow. So that's... Okay. So now, that should be fine, hopefully. Nothing else bad happens. So, thanks everyone for having me back. And I'm glad this time to also be able to talk a little bit more about the research that we do behind all of these elements that are in our workshop. And so I like to always start by acknowledging all of the students and postdocs and all of these scientists who have done this work with me over the years, because I cannot do all of this on my own. And so I now always put this at the beginning, so I don't have to rush through at the end. But a lot of the work that I will show you today was done by Dr. Robbins, Dr. Lee, and Gabriel De Quattro, who is still a student with me. And so I want to start with a quick warm-up question. And so you should find someone nearby to chat with just for a little bit. And let's take about 1 minute, right? Let's see if we can come up with a definition for what is science? How would you define science, okay? So now we have 1 minute. Go. You don't have to be quiet. You're not interrupting anything. I did? Okay.
Sorry, I didn't know that we are going to have exam today. I apologize for this.
Okay, great. So what answers do we have? Okay, Orlando? Is a community for okay. Do we have other definitions? To not fool yourself. Okay. Okay. Yeah. So I would say I probably take maybe a less philosophical view here, if I can. So I like to think about science. This should say science. It's how we systematically ask and answer questions about the world around us. Okay. So physicists a long time ago asked, why do things fall towards the Earth? Biologists maybe ask, how are these different species related, right? This is Darwin's famous observations in the Galapagos. Chemists like to know what the structures of different crystals are so that they can figure out interesting properties. And so we are all here in this room because we see, right, some intrinsic value in this process and doing this. We think it's interesting, we think it's important. But our students need to be convinced of this sometimes, right? So why do you care about the answers, right? Well, we care about these answers because they have impacts on our daily life. So, for example, with climate change, we now get very extreme drought and rainfall. How does that impact the biodiversity with the different species of plants that can survive? This is a big one. How do you produce hydrogen fuel without burning CO2, right? Water splitting takes a lot of energy. And even some really curious things you may have never even thought to ask. So did you know that you can implant pacemakers into dogs with cardiac problems? And I actually learned this the hard way with a little dog, but right, so this is very cool because this is actually just, it's very simple. It's two RC circuits, one is a timer, and the other administers the shocks appropriately, right? Quite simple physics, but really, really complicated science that went into designing this. Okay, so still a little bit more interaction. I want to have some questions that you think are true or false. What do you think? Does science need to be taught the way that I learned it? Because I am a good scientist, so it must work. And so we will just say, raise your hand for true. Raise your hand for false. Yeah, I put some plants in this audience, but you never know. Right? So I would say that if you're here, if you're a professor, even if you're a graduate student, you are what we would call a statistical outlier, right? If all you needed to do was teach science the way we've done it for hundreds of years, why is everybody not a scientist, right? So this is another one. What do we think? Some people are just not smart or dedicated enough to do science. This is why. So who thinks this is false? Start with false. Who thinks this is true? So this is a tricky one, and it's very counterintuitive to most, but all of the best evidence that we have in studying how humans develop suggests that essentially everybody is born with roughly the same potential to become a great scientist, right? And so there's a lot of factors that go into this, and so this is where I was doing some research for this yesterday to adapt locally. I don't know where everybody is from, but if you think about, if you're born in rural Chiapas and you went to public school, do you think you would still be a professor today or a graduate student? Does anyone think no? Yes, maybe. So you can never say for sure, but statistically, the answer is no, right? And as just a great example, this is a study somebody did a few years ago. If you look at parental income versus relative to the country versus the chance of becoming a Nobel laureate, right? So half of Nobel laureates had parents who were in the top 5% of wealth in their countries. And this is not an accident, because we know now pretty well, and it's not too difficult of a connection to make, that wealth is really a key factor in driving educational opportunities, right? So in Mexico, I looked at the OECD report. So if you are from a poor rural area, only 3% of these students even enter university. And if it's a city, it's a little higher, but only 11%. And if you look at, for example, this Chiapas, so only 16% of students from there attend university. In Mexico City, it's almost half. And Mexico City, as I've talked with Isaac about, is in itself very heterogeneous. But this is important, right? Because students who complete a university degree earn about 50% more in their first job than students who do not, right? And so you can see how this cycle can keep repeating itself, right? And so this is also connected to a lot of complex social issues, right? So Chiapas is closer to the rainforest. It has a large population of indigenous Americans, right? But only 10% of these students attend university. And about 35% of these students live in what the United Nations calls extreme poverty. And so this is lack of food, water, housing. So very extreme conditions. And as a result, you see this reflected in things like PISA or college entrance exams. 85% of students who grow up speaking Quechua or another indigenous language score at the lowest level on the PISA assessment, right? And so these things just keep building up and building up over time, but it's not just true in Mexico, right? This is true worldwide. And I have lots of different examples, but take the US, for example. So if you look at who in the United States is getting science or engineering degrees, we have this broken down by different ethnicities, where to the right or left here is underrepresented. And so you can see that bachelor's degrees, master's degrees, doctorate degrees in science and engineering are essentially disproportionately going to one group of people. And this is no accident. So the way this has historically been described, at least in US educational literature, is called this leaky pipeline. And so the idea is that, so you have all of these potential scientists who are 4 or 5 years old, and then you lose some of them at each step of the way. But people have criticized this model, and I think fairly, because it's not really a leak, it's more of a filter. It's not accidental that this happens, right? And so when people think about this, they think about these sort of the situations that these students come from, the socialization, where they grew up, their level of income, and how that impacts all of these things they bring into university with them, which then has this feedback loop with performance, engagement, and finishing degrees. And so I'll give you this framework that we've been using in my research group and characterizing it in the context of the United States, right? So in the United States, we have a long and very complicated history when it comes to these issues, right? But just as an example from near where I live, so things called redlining, which is systematically denying mortgages based on where people lived in certain neighborhoods. Sharecropping, so this was after the end of the official end of slavery, essentially the system was changed so that the former slaves had the opportunity to work the land to try and earn, essentially earn a living for them after the landowner took their share. This still happens in some circumstances, but essentially what this was really done to do was very deliberately prevent them from owning property, from accumulating wealth. And in the US, that has a really, really profound impact. So our school systems are funded primarily at the local level by property taxes. And so if you live in an area where the houses cost more, then more money goes into your schools. So places with poorer residents go to schools with less funding. They have fewer resources, they have low test scores. And then over a certain period, someone decided it was a good idea to try and incentivize them by taking away more money for low test scores, right? And so you can see how these policies have really compounded all of these barriers against these students, such that even when they get into university, and this is what I will spend most of my time talking about because we are thinking about university teaching, is that our students come in with just such different backgrounds, right? Some of them may have never, so in the US, our school systems are very decentralized. Some people have never taken trigonometry before they get to university. Some people, if they come from a very poor and rural school district, they don't know anybody at the university. Other places, big preparatory schools in the city will send dozens of students to prestigious universities. And then there's also this central part, we call it affective or motivational, so just they feel out of place, right? And all of these things are connected with each other, and all of these things are sort of the impacts of how they grew up and where they grew up. And so, this ansatz that we've been working with, right, is that our students come in here, and this is going to impact all of the things that we observe or measure as teachers, right? So test grades, whether or not the students are talking to anybody in the classroom, whether or not the students are doubting whether they can do this. And this is because we are not paying attention to these interconnections. We are letting them evolve naturally, which tends to either preserve things or exacerbate them. And so what we really want to do is think then holistically, knowing that, okay, our students come in here as an individual university professor or even as a university department chair, there's very little you can do about this bottom half, right? And so what we want to do is understand how these connections maybe can be altered or how exactly they impact students. And so I'm going to talk about this with a case study from a large university just to sort of show an example of how this might come out. So we have data from about 16,000 students who began their studies in this 4-year window. We measured essentially whether they completed their degree within 6 years. This is the standard metric that is used in the United States because the longer you spend at university, the more money you're spending. And so we see this as sort of, this is an okay amount of time. And so we had then all of this information that the universities collect about their students. So racial background, what they want to study, entrance exam scores, college marks, if they graduated, when they graduated, what degree they received at every semester that they're enrolled. And so this can quickly cause data paralysis, right? Which is why, oh yeah, so the other thing I'll mention is that the data we have that is taken by the university only measures really these academic things. It is not very good at measuring social or motivational outcomes. These are things that if you want to study, you have to sort of take your own initiative as an instructor or as a department. But because there's so much data, we set out with some very clear hypotheses, right? So essentially we were saying, okay, maybe the leak or the filter is here, right? They've had such bad experiences that they don't even try to study engineering or physics or chemistry when they start university. Or maybe they do start that way, but then you follow this chain where they come in and are less prepared, they get lower grades, and so then they decide to leave and study something else. And so this has been very sort of conceptual, but there are statistical models that you can use to do this. They're called structural equation models more generally, but this particular one is a mediation analysis. And so we use this acronym that comes out of the literature on genetics and biology of race. So peer students, persons excluded on the basis of ethnicity. So these are those students who historically have come from these places that are lower income. You know, they are descendants of people who had overt discrimination against them. And so we say, okay, well, we can observe these disparities, right? We can look at who is getting a degree, but is there some correlation with an intermediate factor or a mediator that is an equally plausible explanation from the quantitative side? Okay, so we do this. So I have these, this is one model. So we looked at, okay, we have these demographics, we have receiving a degree, and so this is, okay, let's see whether any discrepancy here is because they do not even attempt to study STEM in the first place, right? Well, we see some things that make sense, right? So a student who begins in physics, for example, is 4 times as likely as a different student to get a physics degree. There is a fair amount of flexibility in the system here. But counter to our hypothesis, right, these racially excluded students are actually more likely to be these STEM majors when they come in. And it is hypothesized to be because we have been giving this message that this is a way to improve your social standing, to earn more money, to study engineering, right? And so when you account for this, let's say in the context of this study, so a white student and a black student who come in, both of them say, I want to major in science. The black student is only about 67% as likely to complete that degree. And so this is one of the things I was referencing earlier, right? Okay, so we've established that, and so now we look at other potential mechanisms, right? So why is that? So we look at their grades. Our grades are on scale from 0 to 4. So each unit increase in their grades increases the likelihood of completing their degree by 2.5-fold. But these students are earning lower grades in their first year of university, right? But actually, when you account for this, so going back to that same example, a white student and a black student who come in, they study STEM, but they get the same grades, they have about an equal chance of succeeding. And so keep that in mind for a little bit later. And so I like these analyses, but as you can see, they very quickly get complicated. So essentially, ACT, this is our college entrance exam. It's administered by a private company, which is a whole different problem. But so this is what we use for college admissions. And so you see, again, there's a large gap here. There's a correlation here. But also this score is still related to whether or not they graduate. But this number is interesting, right? So if I essentially ignore everything in the middle, and I say, okay, we have, again, the same white student and black student. They have the same ACT score. They have the same first-year grades. The black student is actually about 25% more likely to finish their degree. So this shows that when they come in, if they come in on more equal footing with more equal opportunities, that gap is not there. Because they're more likely to major in these sciences, but they encounter disproportionate academic challenges. But if they are able to overcome them, somehow they are more likely to persist. And so now what we're thinking about, and this is where the problem solving comes in, I didn't forget about it, is that if we can somehow make these correlations go away, this problem could essentially quantitatively go away. And by, I mean on average. We no longer see these trends. So this is our design goal, right? Saying, okay, we can't do much about this. It's pretty unlikely that a student with very low grades will finish their degree. There's not so much you can do about this. Well, there are some things, but we thought, what if we can get rid of this, right? And the idea there being, okay, that we can think about this two ways. One is there some way of increasing this number with what is called supplementary or remedial instruction, right? So can we provide them extra resources to get them up to speed? That's a whole story in and of itself, but the short answer is not reliably. And so then we thought, well, you know, well, what if we change the way we are measuring performance, right? Because when we look at these standardized tests that determine students' college admissions, they don't look anything like what doing science looks like. And so this is where that part of the research comes in, right? Is just the stark differences between what students learn in high school, how they are asked to perform their knowledge, and how science actually happens in practice. So this is a problem from, it's conservation of energy, so elementary mechanics 1, I think. And it's a pretty silly problem, but essentially it is it's conservation of energy with spring force, and you have to find the final speed. They give you all of the information except for v, and you calculate this, and they give you that the surface is frictionless, right? So this, right, you can grade this with a computer. You can have a student, you know, you can randomize the numbers such that every student could get a different answer. But if I use this different example with the students when I thought about how I could teach this course differently, which is I went to this local arcade with these very old-fashioned video games, right? Which is contextually related, but it shows you there's a lot more complexity in the actual system, right? And so this question on the left, yes, it requires them to know conservation of energy, but they have everything they need. There's no real ambiguity in the solution process, which makes it very, very easy to mark, right? Just yes, no. This, on the other side, I figured out, is much more difficult to mark, right? Because it's very poorly structured, poorly specified, right? There's a lot of things that the students will need to decide on, assumptions they will need to justify to come up with an answer, right? And so this is quite hard to grade, even though it is more accurately reflective of what, how science might be used in real life. And so I put a big stop here, because this is a question I always get. Yes, we want them to solve problems like this, but they need to know math, right? They need to know math. They need to be able to tell me what Newton's first and second and third laws are. And I am not disagreeing with that. In fact, at the center of the model we use for thinking about scientific problem solving is what we would call predictive framework or content. And so in our minds, this is a very, very central component. And the analogy I would give is, okay, if someone is very good at solving logic puzzles, that does not necessarily mean they will be equally good at solving physics problems, right? Because there is some knowledge they do not have involved in that. And so the way we think about this is what we call, this is from Dan Schwartz at Stanford. I really like this diagram. So we have innovation, creativity, scientific thinking, if you like, versus efficiency, right? So this is calculations, knowing sine, how it's related to cosine, things like that. And so what we don't want to do is to focus so much on efficiency that that's all students can do, right? Because if you train somebody to do this, that was a large waste of time because a computer is probably more efficient by now, right? And if it's not now, it may soon be. But you also don't want this, right? You don't want somebody who doesn't actually know anything, but just keeps generating idea after idea after idea that won't work. That's not productive either. And so what we want, ideally, is for our students to be somewhere over here, right? We want them to just sort of automatically know, sine of theta plus pi over 2 is cosine of theta. But we also want them to know why that's important and how that relates to creating a structure that is stable or won't fall over, or whether or not something that they've calculated makes sense, right? Because if you get an answer but you switched sine and cosine, it has very different implications sometimes. It might tell you that the strength of a rope required to hang an object is 0 if the rope is straight up and down, if you mix up those two things, right? So this is important. And so what we've been doing is using this template to do what we call this scaffolding, and we mean this in the literal translation of like the construction scaffolding, which is the idea that you give students clues, help along the way. But what we do here that is different is that there are two things. One is that we don't give them clues that are specific to the problem, but instead specific to the process, right? So I'm not going to tell you, hey, don't forget about rotational motion in this problem, but I will say, what are the ideas that you need? What are the physical things happening? Draw me a picture. And so we do that. And the second thing we do is we actually, when we grade or we mark these assignments, almost, I would say about, and I've since changed this rubric a little bit, but 3/4 of the marks on these problems are about the process. Only 1/4 is for doing the calculation. And actually, I give my students, it never seems to work, unfortunately, but I tell my students, if you can do this last part, which is you do everything and your answer doesn't make any sense, but you tell me why, I'll give you all the points, because that is what I care about, right? And so this is a really interesting thing. And so here's an example of how this might play out. So this is a kinematics problem. We're just looking at a ski jump, so it's 2D motion, but unequal starting and ending heights. And there's some constraint that you have to jump this chasm so you don't fall. And so we have students go through and calculate this. And what made this particularly challenging for the students was I asked them to design something. I said, give me some specifications for a ramp that will make sure you can get to the other side. And there's actually there's a finite infinity of possible solutions with these parameters. And I give this solution because they actually did get one of the extreme values of that. But because they weren't thinking about what assumptions they were making or what information was available to them, they missed the fact that that was not the only possible answer they could come up with, right? But because of the process, they got about 80% of the points, right? Because all of the math is correct, most of the setup is reasonable, but it's not what I would say, a complete analysis. And the way we implement this at the scale of a course, right, is through this framework that we've talked about in these workshops called deliberate practice. And so we take this very, very complex idea, so solving a scientific problem, and we break it up into smaller pieces, and then we have these learning activities, right, that support each of these skills or learning goals. And then students complete activities, they get feedback on how to improve. And then this last part is very important, and I will show you an example of what happened when I forgot about it. Or I didn't forget, but I made a miscalculation. And so we have them do this, we introduce this in the first week, and then in the 10-week course, we just go back and over and over again to make sure that they have these skills associated with the content knowledge. Okay, so now I have been doing some what are called quasi experiments. So this is similar to what some of the physics faculty are doing now. Quasi experiment just means that you do not have a perfect control. So in this study, I'm comparing myself and another professor to our same selves 2 years before. And so it's sort of close. It's about as good as we can get. And so we were teaching the same course, so Elementary Mechanics 1. He was using the traditional lecture. He had about 80 students in 2021. This was the first term we were back after the pandemic, and then 160 students. And he kept his course exactly the same both times. So we have these laboratories. Again, that's a whole, not even just a whole talk, that's a whole different branch of research. So we didn't do anything with those. He didn't have attendance or interactions in class. They just had a weekly quiz, small homeworks. They had 4 exams. So this, what you would call the global exam, we had a similar thing. So he said this is 25% of the grade and the others are 45. Unlike, well, actually this has since changed because students have been complaining. Before we were allowed some freedom here, right? And so I did not weight this exam very highly because it did not incentivize the kind of thinking that I wanted, but I left it big enough to change a student's letter grade so that it gave an essence of fairness. But I had them come to class, so there were 36 class periods. It was worth about 1 letter grade. So the theory here is that, okay, if you don't want to come to class, if you do perfect on everything else, you can still get the highest mark, right? But I'm going to incentivize you pretty strongly because what are the chances of being perfect otherwise, right? And I also gave them some relief. So I would say, we will disregard the lowest exam, the lowest homework. But then when I did this again 2 years later, thinking back to my own advice on deliberate practice, you'll see there's a lot more letters here. I played with some of the percentages. But the big thing I did is I reduced the number of exams and the number of homeworks substantially because I let the students resubmit every single one. And so the way this would work is they would have about a week to do a homework. They would turn it in. The ayudantes had to grade it within 4 days. and then the students get their grades back. The grades are very coarse, right? So about 60% of the problems are just graded, you didn't turn it in, you tried, and it's pretty good, right? And then we did give some more detailed feedback, but they could then resubmit the assignment, and mathematically what we did was average the 2 grades. To make the burden a little bit easier for us, the resubmissions were just sort of graded as, you get your points or you don't. So it would never lower your grade, but you had to have essentially a perfect solution to get the points back. But our argument was, well, you've had 2 weeks, there's 5 teachers, teaching assistants, 1 professor, all of these hundreds of other students to talk to. You should be able to get it within that time frame. And so this turned out to be a very important piece, because we are looking at a simpler representation of these diagrams I was showing earlier, which is grades in physics as a function of college exam scores. So blue is me in 2021, my first ever term teaching on my own. Green is me 2 years later, and then the lecture is gray 2021, orange 2023. And so we did what is called a moderation between these 2 variables. And what that means is that we changed the y-intercept, if you like, right? So we raised everything on average, but we also reduced the slope, right? And so the reason both of those data points are important is because you could think of a different scenario where maybe this green line crosses these other 2 for some strange reason, right? So the lower performing students did better, but the higher performing students did worse. I've never actually seen that happen in practice, but it is a concern I always hear. So it is good to just verify, no, we helped everybody, we just helped these students a little bit more, right? And so we connect this back also just to the observational gaps. So we look at the top and the bottom half of incoming college entrance scores, and then also break it down by ethnicity. And we see here, for example, the green. So this is the 2 different shades of green are the different racial groups, right? And so we see it's closed here, but it's also closed statistically across all 4. But not quite so with the blue, right? So yes, within preparation it's closed, but not quite across, right? So there was still some variation there. And we also looked at some other demographic variables, because in engineering we're very worried about representation of women as students whose parents did not go to college. But what this indicates to me is that this is what makes the practice deliberate, right? Because in theory, I was providing them all this feedback, right? They could have acted on it, but if I didn't incentivize it, they wouldn't do it, right? And so this is the same thing as saying, to a student, oh, well, go back and look at your old homeworks, look at the mistakes you made. It's great to say that, and ideally everybody would do it, but just incentivizing it was a way to really affect that change. Yeah? Yeah, sorry.
When you change the way you are working, do you have an idea of what the change you did from apps AAP to EA is one, yeah? What has the biggest impact?
So I think what has the biggest impact is being able to revise all of the assignments.
What is the increase attendance, right?
And yeah, a little bit. Yeah, by a little bit. I did that. Now I don't remember why I did that. I think it was because I wanted to signal that participation was an extremely important part of the process. And so I wanted to make it then very clear, no, you have to come to class, you have to participate. We can talk about whether or not that was successful. And there's a lot of other data we have from this class. We did some, actually, the statistical physicists would love this. We built some networks and we did graph theory, topology analysis on them. It was very, very interesting stuff.
So then for you, the highest impact would be the fact that they were able to resubmit.
Yeah, yeah, and they right.
This kind of a skeleton.
Yeah, so they could resubmit everything. And the important part of this is not just they get their points back, but we also know that this is an important part of the learning process, right? Is getting the feedback and then using it to revise your own performance. And so this, in hindsight, this makes a lot of sense, right? Because even though they were practicing the same problem solving as we went, it was different content every time. And so you need to have them reflect on both. So you want them to solve real world problems, but because it depends on content, you need to have ways for them to think about both simultaneously.
But you have to listen to the system properly because as I told you, I tried this thing.
Yeah.
Mm-hmm. And they could resubmit as many times as they wanted until the end of the trimester. And what happened, they waited until the end of the trimester because they realized they were not going to pass. And they were fishing for marks.
Yeah. So Isaac was giving an example where you take this to a point where essentially you have unlimited attempts and you take as long as you want. I could see this working in a very specific context, and I've heard of like elementary school teachers who will do this, but that is a very different classroom. It's a much more personal relationship with the students than is really practical, especially, here I had 158. Well, the next term I had 244. So it's getting harder and harder to do things like that. But I also told the students, I'm doing this because I think it's good for your learning, but I have to draw a boundary because there's only so much time we can invest in this. Okay, so this last part, I have no idea what time it is. So this is an interesting opportunity that came up actually about the same time, which I was invited to do something a little bit like this down at the Escuela Politécnica in Quito, Ecuador. And the department chair invited me there, and I gave a talk, I gave a workshop, and we had started building this because they actually do not have teacher education programs. So in the US, for example, you can get a bachelor's degree in physics and a master's degree in education, and then you are a fully licensed physics teacher. They have nothing like this in the country. And also when we talk about access, this is all of Ecuador is mountains and forest. So a lot of their students live in these extremely remote regions, right? So both of these places were about 100 kilometers from Quito. It took 5 hours to get here, and it took 3 hours to get here. So it's very remote. And so access to education is a problem, and they're seeing this very rapid population decline because the people who want more chances, they have to leave, right? And then when they get the education, there's nothing to go back to, and you see the same thing happen over and over again. And so the idea is then, okay, we are now working, and fingers crossed, it will start in March, is this master's in Maestra en Física Educativa. This is a 1-year master's degree program that we designed, and it is based entirely, so the work I was doing is part of what's called physics education research. People have been doing this for about 50 years now. And so the classes that we built in here are based on these decades of research on what students have the most trouble with, how to address it effectively. And so the idea is these teachers will sort of be getting cutting edge training in most effective teaching. And so then what we are trying to do now is establish some partnerships between the students in this program and some faculty and teachers who come from these rural areas. I should have switched these, but even before we are getting to this part, following the workshop I did 2 years ago, they started implementing these tutorial sessions. And so their failure rate dropped from over 40% to 18%. And the students who attended at least 3 of the tutorials, not a single one of them failed. Not a single one. I think failing is maybe 5 out of 10 there instead of 6 out of 10, but still, you know. So this is really astounding, and there's some other results there. But what we're trying now to do is get funding from an educational foundation where we can build this cycle, right, where this master's program is connected with this conference that I was attending, and we work with these teachers to sort of figure out, okay, what are your needs, right? And then these teachers, we come and we pay for them to come and attend this conference, and we have this national physics teacher chapter that we build there that they can communicate through. And then we connect these two things and we try and create this cycle that continues to support them. Because currently, all of the progress is put on the department chair and then me and one other consultant who come in every 2 years, and this is not sustainable long term. And so what we're trying to do is get a little bit of money to jumpstart that and build the infrastructure. Okay, so that's all I have prepared for today. I'm happy to answer any more questions you might have.
Questions?
So, we talked a little bit about this paragraph, whether remediation works or not. Because I think that's one idea that we have several years trying to do here, and I don't know what are the results in your opinion. What do you think about that?
Yeah, so I think remediation could work in some circumstances. The problem is that there's not enough concrete evidence to tell us what is needed to make it work. So simply having them come in and attend additional lectures or even practice extra problems does not seem to be enough. At least not for everybody. But, and people have tried some other things. They've tried things like, very simple things like, make sure you write down when your classes are and when assignments are due, these sort of executive function kinds of things. But there are so few experiments that are not subject to a selection bias, right? So the people who say, oh, I should take this extra help is not necessarily the people who need it the most, right? And so it's very hard to get clear data on what makes that work or not. And so I'm not saying it couldn't work, it's just that I don't think I could tell you what you need to do to make it successful. It would be very interesting research, but the students may or may not be happy about not being sure if it's going to help them.
But even if you do this remedial courses using active learning?
Yeah.
Even.
Yeah, so the results I was talking about, I think even one of those semesters, I think, was taught by Carl. So, you know, so even people who are quite expert and experienced, it did not do this change in slope that we wanted. What it did was, I think it raised the intercept, right? But it didn't help the students who needed it the most. So it was still, it's not that it wasn't helpful, it just wasn't enough to get all the way to where we wanted to be. Yeah? Orlando?
Having remediation process before the trial process works better or worse that give that remediation on the fly during the course itself?
So the question was, should remediation come before or concurrent, right? Or alongside? So the models or the data we've seen, at least from the university that I was studying here, we looked at some of this data in mathematics. And what we found was that even the students who did very well in the remedial course were still less likely to finish their degrees. I don't have a very strong explanation for why. What I think is probably what happened is that they say, oh, I got an A in trigonometry, and then they're still getting a C, or sorry, I'm getting a 4 out of 4 in trigonometry and a 2 out of 4 in calculus. So clearly, you know, this didn't help, or I'm not cut out for this, even though 2 out of 4 was the average in the class, right? So there is a psychological aspect to that. I think the concurrent side-by-side models could be very helpful. The only problem there is that you're adding more time on top of what the students are already doing. I mean, in an ideal world, it might be nice to have students who are able to say, okay, you know, I need some help to catch up, so I will take just physics and just calculus, and I will take them each for 6 hours a week, right? And those are the only 2 classes. The modern university does not work to allow that very easily. So when we've asked students, they said the most they would be willing to devote is about 2 extra hours per week.
Is when you change the structure of the grade, I sometimes worry that when I do that, the students get better grades just because I'm running walk the grade is good. So some of them get higher and some of them down. They in the end they just cancel out. Do you have any evidence to the contrary that it's still because there is an actual beneficial mechanism, not just that because they have more opportunities to get involved?
So there's an interesting balance there between lessening anxiety around grading and giving them more opportunities, but also making sure they're still learning. I don't pretend to have an exact number. Somebody did what's called an observational study, so they looked at correlations. And so, for example, I think she found that if 50% of the grade was exams and 50% was something else, then that seemed to be about the right mix. But it's very hard to study that in any kind of controlled way. So that's something that I think, I mean, honestly, what makes it the most fair is something like what you do with these global exams, which is this much of the exam, everybody has to do, it has to be the same. The rest you can do what you want, right? So I guess your coordinator may not be happy. You could say, okay, the other 5 points, everyone gets 5, and you start at 5, and then you. But that's of course an extreme case. But yeah, so for example, even when I did these experiments, I could actually no longer do the version that I tried because now we are mandated that 60% has to be exams, 20% has to be the global exam at the end, 10% has to be labs, and so you're left with only 30% that you have control over. And this was decided by committee, so I think if we all decided that's what we want to do, that's fine. Yeah.
But now you have this thing, you have this constraint, and how are you going to handle this constraint?
I don't know. I haven't had to teach this class with that framework yet. In fact, I may not have to do so for a number of years. That was not planned to coincide that way, but.
Okay. More questions?
Lydia? So the question was about this, is it wise to have this one large exam at the end or smaller exams along the way? This is, again, there's a balance, right? Because there is an educational value in studying for a comprehensive global exam and reviewing all of these things. What happens in the exam room, I could not even pretend to speculate on, because I've graded these and seen, I know this student knows this perfectly. I have no idea what they wrote here, but it's it's not what I saw a few weeks ago. So there is some element of pressure there that definitely affects student behavior, but I do think having some kind of comprehensive assessment is helpful. So there are the other extremes, like the German and Scandinavian models, where you take a class and there is one exam at the end and that is your grade, right? Very extreme. I don't know why you would bother going to class, but but then, so generally speaking, I think fewer exams in the middle is better, but it's still good to have something at the end. And so I know some places will do this thing where if you already have 9 out of 10, or I guess 8 out of 10 is the divider. If you already have 8 out of 10 going into the exam, you don't have to take the exam.
Sorry. But the title said, can we make science more accessible by teaching real-world crap? And so sometimes I feel that I should be really teaching them with drones, or the computer, that. And the feeling that I have is that not everybody is interested in those. There is a huge variety of interest. So when I speak of rockets and Pluto and galaxy, whatever, more than half of the class sleeping because they don't care. So the question is, how to deal with the diversity when we teach real science to them?
Let me add to this thing, because
Okay.
just to give more information, because we are in our courses in this in physics, in these core courses, we have students that are going to the bachelor's degree in physics,
Yeah.
computation. So there is a variety of interests, and one of the questions, how come we pick up the interest of a good percentage of all?
Yeah, that's a very good question. And I will, you recognize I didn't really answer the question. It's not a simple yes or no answer, I think. But it's good to think about. So when dealing with a variety of motivations is always difficult, and the best approach that I have is to just have a wide variety of contexts within an individual unit. So for example, in static equilibrium, we do not just talk about bridges, we talk about joints in the human body, strength required to do exercises, trying to think of, sometimes we do fun ones, like there's these videos of a car has fallen into the harbor and they send a tow truck to come get it, and it connects, and then the truck falls in and they have to send another truck. Is actually a very simple torque problem. The bigger truck isn't actually heavier, it just has the stabilizers on the side. But this is a fun example. Yeah, so using variety is helpful, because you're right, not everyone cares about rockets, not everyone cares about space, and so we have to recognize that and meet the students where they are. And so I try as much as I can. At least in elementary mechanics, it's a little bit easier, because you can say, here is something, the table rocking back and forth, right? You can feel that. Your body doing an exercise, you can feel that, you can see it. And it's a little bit more universal than a rocket, and so they have some better sense of it. Of course, it gets more and more difficult with electricity, electric fields and quantum mechanics. But my thinking is that by the time they get to quantum mechanics, that you probably don't need to sell them on physics anymore. They're probably fine. Yeah, so you do need to be thoughtful in doing that. But even if you are using examples like rockets, trying to find something local is helpful. So if I'm asking about stability, I will go around campus and take a picture of something and say, this building is going to fall over. Can you tell me when it will? Or, the students, I don't see it here. Yeah. And I've not seen it on campus, but I see it where by the hotel, these scooters, right? So right by my office, we have this big hill, and students try to ride the electric scooters up, but the motors do not have enough power. And so they eventually stop. And so I say to the students, how much power does the motor need to maintain your speed up the hill, right? So then, even if they don't particularly care about the answer, they can at least see why it's important and where these things are used. Yeah, so that's my thing. So use a variety, and when in doubt, use things that are very, very real, things that they see every day or very regularly. So I will, Marco's not here, but he had this example for rolling with the ab wheel. Do you know this? You pull forward. It's actually extremely difficult, but but yeah. So this is this is an example. It's like, oh, this is how rolling works. So you bring in the bicycle wheel, and you can even do more complicated. Bicycles are very complicated. I had students do these things with gear ratios and all of this. It would have been helpful if I had a real bicycle with me, but. Thank you so much.